so yeah, so I will talk about, the title of my talk is The Tropical Twist on Hurwitz Numbers. Thanks a lot for the organizers for inviting me. So I will report on joint work with Hannah Markwich, and this is part of a longer program that has now been sort of joined by Raphael Fessler and Max Karev. So they were sort of working independently on similar things, and then we heard about it, and then we joined forces. And yeah, so this is some sort of ongoing program. And before I start with my talk, I just want to make two public service announcements. So so me being in Dublin, I have the great pleasure of being simultaneously the worst and best tropical geometer in the country, because I'm the only tropical geometer in the country. Well, the best, maybe not anymore, because I have PhD students now. But if you want to join me being a tropical geometer in Ireland, in Dublin, so every year there are these grants. So there's the IRC postgraduate scholarship. So this is for people that want to do a PhD. And there's also the IRC postdoctoral fellowship. So these are pretty competitive. But the workload to actually get one of these grants is quite minimal for you. It's a lot of work for me, but for you, it's not a lot of work. And so, yeah, if you're interested in coming to Dublin, feel free to contact me. There's also more information on the website. But this is a good and sort of like minimal effort way of getting a grant at a like early stage of your career. Okay, so let's come to the math. Yeah, so the title is A Tropical Twist on Hurwitz Numbers. I completely stole this from one of my co-authors who wrote a paper which is called A New Spin on Hurwitz Theory. So in his paper, the Hurwitz numbers are called spin Hurwitz numbers, and then so in this work, the Hurwitz numbers are called twisted Hurwitz numbers. So it's a complete plagiarism of the wordplay. And maybe I will be brave enough to remove the conference announcements. It's also explained on the website. I looked it up yesterday. All right. Yeah. So some of you might have seen me give a talk before about Hurwitz numbers, and you might ask yourself, why doesn't Marvin just leave them alone? And so I have the feeling that they won't leave me alone, because every couple of years some new exciting development happens. But let me first start with the basics. So the thing we're going to be interested in are so-called double Hurwitz numbers. And I first want to tell you what the classical story is. And so I'm always going to abbreviate Hurwitz numbers like this. All right, so what do the double Hurwitz numbers do? So double Hurwitz numbers do the following. The definition is, let G be bigger or equal than 0, D bigger than 0, and then you take two partitions of D. And then double Hurwitz numbers Hg of mu nu. So they count the following set in a stacky way. So by taking automorphisms into account. So it's all maps from a genus G surface, right? So like this is of genus G. And I'm going to be imprecise whether I mean this to be a connected surface or a possibly disconnected surface in the talk, because this is just a technical detail. This just corresponds to taking the like log or something. So it doesn't really change much of the things I'm going to talk about. Yeah, so like this is the situation. And so you look at degree D maps from a genus G surface to the Riemann sphere, where you fix that the ramification profile of 0 is mu. So this is the ramification profile mu. And here, over infinity, you have ramification profile. All right, so let me quickly explain what the ramification profile is. So holomorphic maps between Riemann surfaces have the wonderful structure that they are locally polynomial. So you can always choose local charge such that this becomes a polynomial map. And then the ramification degree of a point on this surface is the degree of the local polynomial. And then the ramification profile is the tuple of all the ramification degrees in the pre-image. All right, and then you do one more thing, and this is just a number imposed by the Riemann-Hurwitz formula. So take R is equal to 2G minus 2 plus length of mu plus length of nu. And you just fix R many points, right? So you pick P1, a bunch of points all the way up to PR, and then you force all these things to be simply ramified, then the ramification profile 2 and then only once. All right, so these numbers, well, sort of slightly simpler case, but essentially these numbers were introduced by Hurwitz in the late 19th century. And I think the motivation originally, so he's kind of wary on like what his motivation is. So he starts his paper with like, obviously this is a very, very interesting question. But I think the motivation was he wanted to prove that the moduli space of genus G curves is connected. So, sorry, not connected, irreducible. So that was an open question at the time. So of course, this was proved using different methods later on. But the original motivation was somehow, well, if we can understand the coverings of a genus G surface, or of a genus G curve, mapped to a Riemann sphere, and if we understand the structure of these numbers, then maybe we can show that they have to live in the same space, because otherwise, like, I don't know, some sort of structural properties are going to break. All right, so in this work, Hurwitz already made a very interesting observation. And so in modern terms, this is of course simply the monodromy representation of the topological covers. But back then, he actually had to do it by hand. And so the theorem that Hurwitz proved, and I can never remember. So I think this was 1891. So Hurwitz proved the following. Namely, hg of mu and nu is equal to 1 over d factorial. Sorry, I probably should have said that this is a, oh, no, I did say this is a degree D map. All right, and so of course up to like some sort of isomorphism. All right, so double Hurwitz numbers are equal to 1 over d factorial times the cardinality of the following set. Now this is a set of tuples of permutations. So you have sigma 1, tau 1 to tau b, and sigma 2, such that the first thing is that all of these things live in the symmetric group SD, right? So the degree of the map corresponds to the symmetric group that we live in. Sorry, this is supposed to be R, so it's the same R as before. So the second condition is that the cycle type of sigma 1 is equal to mu, and the cycle type of sigma 2 is equal to nu. So what this is this is the partition corresponding to the conjugacy class of sigma 1 and sigma 2. And so similarly, the tau i's, they are transpositions. So what's the cycle type of a transposition? Well, it's 2 and then only once, right? So this is exactly what the correspondence is. And the last condition is that sigma 1 times tau 1 all the way up to tau r times sigma 2 is equal to the identity, right? So this, I think on first sight, quite complicated geometric problem can be translated to a simple factorization problem in the symmetric group that in principle every, I don't know, first year, second year student should be able to compute in some simple examples, right? Yeah, so also when I saw this for the first time, I don't think it's obvious that this is a finite number, right? So if you classify this up to isomorphism, could be that this is an infinite number. The first proof of this historically, that this is a finite number, is this, right? So this is the proof that this is actually a finite number. And so I personally, I only know 2 proofs. So this is the one, and the other one is using tropical geometry. I don't know an intrinsic geometric proof of the fact that this is a finite number, but maybe there is one. All right, so this is the classical story, and this is like 100 years old, over 100 years old, and so Hurwitz introduced this, and he wrote 2 papers about it, and then no one cared, basically. So for 100 years, no one cared, and then in the 1990s, people started to really care because these Hurwitz numbers are connected to Gromov-Witten theory, right? So there's the very famous Eckeder-Landau-Shapiro-Weinstein formula, which says that single Hurwitz numbers, so nu being the trivial only once partition, is equal to some intersection product on MGN involving the total Chern class of the Hodge bundle and so on. And so this actually allows to compute these Gromov-Witten invariants just using some sort of very basic group theory. All right, so now, so I've explained what Hurwitz numbers are. So the title is a tropical twist on Hurwitz numbers. The next thing I'm going to explain is what a tropical Hurwitz number is. All right, so So Cavalieri, Johnson, and Markvich in 2008. So at least it appeared on the archive in 2008. And I think, oh my God, I wrote Renzo's name wrong. I'm very sorry if Renzo watches. I should know what his last name is written. It's still wrong. What? Okay. Oh yes, but no. Okay, let me actually. Oh, sorry. No, it's Caval. So this is the name. All right. So sorry about that. All right. So all right. So they developed something which is called a tropical Hurwitz number, and then they proved that tropical Hurwitz numbers are the same as classical Hurwitz numbers. So I don't want to do this in the most general setting. So I don't actually want to give you the definition. I'd rather work out an example. All right. So let's look at the following example. Right. So the example is the following. So mu is equal to the full partition 3. So of course d is equal to 3 here, and then mu is equal to 2, 1. And then I think I chose g is equal to 1. So the first thing we have to compute is r. Right? So r is equal to 2g minus 2, which is 0, plus the sum of the length of these partitions. So this is 3. All right. So what do we do now? Well, we pick a tuple satisfying these conditions. And so sigma 1 in here is equal to 1, 2, 3. And tau 1 is equal to 1, 2. Yeah, so tau 1 is equal to 1, 2. Tau 2 is equal to 2, 3. And finally, tau 3 is equal to 1, 2 again. And sigma 2 is equal to 1, 2, 3. All right. And my claim is, so this is something, well, I might have made a mistake in these computations, but my claim is that this satisfies these conditions, right? So the cycle type conditions are immediate. This is cycle type 3, and this is cycle type 2, 1. It has the correct number of transpositions, and then the product is equal to the identity. You can just check for yourself. All right, so what do we do now? How do we get a tropical picture? Well, you start with 1, 2, 3, right? So, and you just draw an edge. And so then you multiply by tau 1 from the left. And if you multiply by tau 1 from the left, this cycle splits up into a cycle 1, 3 and a cycle 2. And then you multiply with 2, 3, right? So like every vertex in this graph is going to correspond to one of these transpositions. So then 2, 3 is going to rejoin these cycles, right? And so the new permutation is going to be 1, 3, 2. And then again, you're going to split this up into 1 and 2, 3. All right? So, and that is the basic idea. And now what you do is you forget what the permutations are. You just, so what the cycles actually are, you only record what are the length of these cycles, right? So, and the graph that we get in the end with a map to the tropical projective line to record the order of the vertices is the following. So it's 3, 2, 1, 3, 1, 2. Okay. And so the theorem is the following. So the theorem, I'm not going to retry writing all these names. So this is just saying that Hg of mu nu is equal to the sum over all tropical covers from some graph gamma to the tropical projective line. So they are weighted by 1 over the order, so let's call this pi. So they are weighted by 1 over the automorphisms of pi. So these are graph automorphisms that respect the weights and that also respect the map times the product of the inner edge weights. Okay, so let's work this out for this example. So in this example, this is just going to be 2. So there are no automorphisms here because these things have different weights. If this was 1, 1, I would have an automorphism. Similarly here, but so I have no automorphism, and the inner edge weights are 2 times 1 times 3. So therefore, the contribution of this right here would be equal to 6. Then you just go over all possible things. Oh yeah, let me mention. So for those people that have never seen this before, so the key requirement is that everything satisfies the balancing condition, right? So 3 is equal to 2 plus 1, and so 2 plus 1 is equal to 3. All right, so that is the basic statement here. And yeah, so as I said, this is kind of yeah. So in the early years of tropical geometry, and so since then, so especially in the last 15 years roughly, a lot of variants of Hurwitz numbers have been discovered. So this arises in a bunch of different contexts, but most of them actually use the representation theory of the symmetrical. And like, I don't know, like, so I'm going to talk about them in a second, but so one variant, for example, monotone Hurwitz numbers that I worked a lot on basically correspond to imposing some conditions on these transpositions. And so you can still do tropical geometry for these things, but it's much harder. So, and the reason is basically that what is really lurking in the background, so what's really going on here is that the theory of symmetric functions and the theory of shifted symmetric functions actually shows up and governs the combinatorics. And so what I only like really understood in the last few years is that a lot of this is basically just base changing with respect to different generators of the algebra of symmetric functions and the algebra of shifted symmetric functions. So you can express like, so, and this is where a lot of the expressions relating Hurwitz numbers and relative Gromov-Witten invariance come from, because relative Gromov-Witten invariance, so I'm not going to properly get into this, but I just want to mention it. So relative Gromov-Witten invariance correspond in the algebra of shifted symmetric functions to the so-called shifted symmetric power sums, whereas classical Hurwitz numbers correspond to something which are called central characters. So, but these are both generators of the algebra of shifted symmetric functions. So you can sort of just like base change in this way. And this is basically where this entire relation between Hurwitz numbers and relative Gromov-Witten theory comes from, that also Okunkov and Pandey worked on in their relative, so in their Gromov-Witten-Hurwitz correspondence. So this is just a sentence for the people for whom this means something. I'm going to be a bit more basic, but I'm still going to talk about Hurwitz theory and symmetric functions. Okay, so let A, so we're going to pick two infinite sets of variables. So semi-infinite because they all start somewhere. All right. And then we consider the following generating series of double Hurwitz numbers. So this is called a tau function, because Okunkov, oh yeah, so this may be something that I also should have said. So Hurwitz really studied the case where this right here is trivial. And then double Hurwitz numbers were introduced by Okunkov in 2000. Yeah, so in 2000, because the generating series I'm going to write down now is basically a solution of the 2D total lattice hierarchy. So you can use Hurwitz numbers to construct solutions of integrable systems, but these are not going to be actual regular solutions that show up in in the actual real world. These are just formal sums. But this is where the entire theory of Hurwitz numbers, of double Hurwitz numbers, originated. And the generating series is the following: sum over all the d bigger or equal than 1, and it's z to the d times the sum over r bigger or equal than 0, u to the r divided by r factorial times the sum over the hg mu nu times p mu of a times p mu of b. So what is this? So pi is equal to the xj to the aj to the I, and then p mu is equal to the product of all the p mu I, where the mu i's are the entries of the partition indexing this, right? So like this is just a way of packaging this as a generating series expanded in symmetric functions. And now I think I finally have to succumb to cleaning the board.
Ich hole dir gerne.
Nee, ist alles gut, alles gut. Sorry, can you say it? Oh, this. Oh, sorry, I forgot to say this. Okay, let me first clean everything else, and then I will say what it is. So it's the sum over the partitions of D. And so because we've already fixed R, G is also fixed. All right, so that's basically what we have. But I should have at least written what G is. All right. How am I doing with time? So, all right, that's okay. Okay. Yes, so as I said, what I want here is that these are partitions of D, and then by the same formula as before, R and G determine each other. Okay. So as I said, right, so you have this really interesting work of Okonkov, and we've understood this theorem much better now. So Okonkov, in some sense, really worked this out by hand. We know nowadays that what we get here is a hypergeometric tau function. Then this connection to integral the system becomes, so like you basically get for free, but tau yields a solution of the 2D total lattice. And the 2D total lattice you already saw in the talk of my PhD student, Vincenzo. Okay, so what's the key idea now? So the key idea is, as I said before, this is just some generating set of the algebra of symmetric functions. So how about we expand this in a different generating set? Okay, and so one other generating set are the Schur functions, right? So these very naturally show up in the symmetric function theory and also in the representation theory of the symmetric group. So let's expand in Schur functions. And you get a much cleaner representation here. So of the series. So in that case, tau is equal to the sum over all possible partitions lambda. And then you have a function y of lambda times s lambda of A times s lambda of B. And this function, I can explicitly tell you what it is. So this function is, I can never really remember it. So it's a product over all the boxes in the Young diagram corresponding to lambda. Then it's z times e to the c. So this is the content of the box. I'm going to say what it is in a second. So, and this right here is the column index minus the row index. Okay? And this is now really the basis for a lot of the symmetric function theory applications to Hurwitz theory. I see that also still exists, so I should have removed that as well. So it's not super important that you exactly understand like what this function is. The important thing that you have to understand is the shape of this expression, right? So you start with I will admit, quite horrible generating series of double Hurwitz numbers, right? So there are certainly much easier generating series of these enumerative invariants, but then when you just choose a different generating set of the algebra of symmetric functions, you suddenly get a very clean expression. So similar things hold also for other enumerative invariants. So for monotone Hurwitz numbers, so this corresponds to the following. So this counts these things again. So these tuples of permutations that I had earlier. so same conditions, plus an extra condition. For tau I, you have equal to, so which is equal to, so AI is bad now, so CI DI, where we may always assume that CI is smaller than DI, we impose that DI is smaller or equal than DI plus 1. Right, so you just count the same tuples of permutations that satisfy in a like one additional monotonicity condition. And so these numbers, so these monotone Hurwitz numbers, so these are written like this, HG mu with an arrow on top of it. So these show up in random matrix theory. So just naturally, so Golden, Guy-Paquet, and Novak worked this out in 2011. So if you look at a very specific matrix integral, which is called the Harish-Chandra-Itzig-Zubair integral, and you look at the asymptotic expansion, the coefficients in the Taylor expansion are these numbers, right? So this is really some sort of miracle that's going on here, that these very old numbers suddenly show up in random matrix theory. So you can do the same thing. So you can define again a tau function in the very same way. So okay, this looks a bit different. And here you have the monotone Hurwitz numbers, but let's skip the details. But what you get here is that this is once again the sum over all partitions. And then now you have a monotone variant of this function y of lambda, s lambda of A times s lambda of B. Okay, and what this function is so this is the product over the z. So once again, over all the boxes in the Young diagram corresponding to lambda, z over 1 minus c of the content of that box times t. Now, right? And I just realized I always use t instead of u. So this should be u. Yeah, in my early notes, this was t. So sorry about that. But that is what's going on here, right? So once again, you have an expression like this. And let me also mention, so if you look at relative descendant Gromov-Witten number, so if you look at these numbers, but you always have the same R. So you always have to fix the same R of the descendant insertion. So if you look at the corresponding tau function, then you also get an expression, so which is y Gromov-Witten of lambda, s lambda of A, s lambda of B. And now this I don't want to write, but this function essentially is induced by e to the pk bar, and these are the shifted symmetric power cells. So we know what these functions are. It's just a little bit messy to write them down on the blackboard. Sure.
Multiplier y of lambda. In the KP theory, they would be points in the Sartre-Glass model.
Yes, I don't think it's obvious, but it's true. But I don't think it's obvious, because what you get here is something which is called a hypergeometric tau function. So this is really the tau function. Well, I think maybe the log of this is the tau function, but okay, up to some details. All right. So there's a paper in the early 2000s by Orloff and Sherbin. And Orloff and Sherbin, so they call these tau functions really hypergeometric tau functions because they come from hypergeometric functions. So you can use hypergeometric functions to construct tau functions of the Toda lattice. So the KP thing comes when you specify B to B1 is equal to 1, everything else is equal to 0. So then you get something for the KP. But yes, so the answer is yes, but this is a serious paper by some Russian mathematical physicists. So okay. All right. So now let me say sort of like a very general theorem. So which is not really a theorem, but more like a philosophical statement. But it's Friday, so I shouldn't be too technical, right? So okay, so we have Cavalieri, Johnson, and Marklich, and so then it's also Druve. So or as I like to call them, Hannah and friends, and then it's also me and friends. So the Danilo Levansky, who comes from the topological recursion world, and then many other people. Let's say that all of these numbers have tropical interpretations. since I am giving the talk, allow me to highlight one of my theorems that I proved in the past. So if you look at these monotone Hurwitz numbers and you look at the tropical interpretation, you would expect just from the structure, right? So I showed you earlier. You just start with the tuples of permutations, then you draw this tropical graph, and then you like get this number. And for monotone Hurwitz numbers, I just do a subcount. So you would expect that the natural tropical interpretation is just the subcount of the tropical maps. This is absolutely false. So I tried this during my PhD thesis, and I wrote something about it. But what became clear is that this is actually the wrong tropical picture. The right tropical picture is actually going through this symmetric functions, and I did this a couple of years later. And then what happens is the following. So you get tropical covers, which have a much higher valency, so at the vertices, and you get vertex contributions that are relative Gromov-Witten invariants with target P1. So I have no geometric reason for this, absolutely none. This just like naturally pops out of the symmetric function theory, right? So you just expand your symmetric functions in a different basis, and the coefficients suddenly become relative Gromov-Witten invariants. So, all right. So what's the moral of this story? So sort of morally, the following should be true. So if we have the sum over something times S lambda of A times S lambda of B, then after expanding, into P mu of A and P nu of B, we should have a Hurwitz type and also tropical interpretation. Okay. Yeah. So that is at least what it feels like morally. And so like, of course, the condition is that this is like sort of sufficiently nice. Right? So this can't just be anything. And probably the answer is, in this setup, it is just going to be shifted symmetric functions. But I don't know yet. That is work in progress. All right, good. All right, so that is kind of everything I wanted to say about this. What I wanted to tell you about, so I really want to get to these twisted Hurwitz numbers. So let me tell you very briefly about the motivation for the introduction of twisted Hurwitz numbers. So this is this Golden-Jackson B conjecture, and this is an open problem. Okay, so what's the Golden-Jackson B conjecture? So the idea is, let's not take triple products. Sorry, let's not take double products. No, that was the like punchline. So let's not take double products. Let's take triple products of Schur functions and try to see what we get, right? So we started with an enumerative problem, and then we expanded it in Schur functions. So the Golden-Jackson B conjecture starts with a classical observation that you can start with Schur functions and you actually get numbers. So you actually get something that counts something. All right, so let me write this. So let's tau be equal to the sum of the lambdas. And okay, so out of interest in time, I'm not going to tell you what the coefficients are. So you can think of these as combinatorial factors. For the people that know something about this, this is the product of the hook length in the Young diagram of the partition. And then T to the size of lambda, right? And then so classical factors, I have no idea who proved this. I tried looking it up for this talk, but I don't know who proved this. So if we look at these triple sums, what we get is that this is sum over the T to the D, sum over the alpha, beta, gamma, partitions of D, then the size of the conjugacy class in the symmetric group of gamma divided by D factorial times, and now here's the key. So we're counting Hurwitz numbers. So again, we have some cover here, but it looks a bit different maybe it looks like this. So we have 3 ramification points and only 3. We don't have any simple ramification. And this is going to have ramification profile alpha, ramification profile beta, ramification profile gamma. And then we multiply by p alpha of A times p beta of B. All right. And so I switched to alpha, beta, gamma is because while preparing the talk, I didn't remember what the Greek letter after nu is. So, but I do need 3 partitions here. Okay, so like this is something that we already know. And so I started out really structured with the blackboard. Now it's just a mess. I'm sorry about that. Okay. There's no dependence in C. Sorry. Oh, I see. Sorry, I just forgot to write that. Thank you very much. All right. So, all right. So like this is known, but I promised a conjecture. So what's the conjecture? So the conjecture, I'm going to state this with a black box. So in the black box is, let's actually maybe write that. The black box. If you want to learn about this, there's a wonderful book by MacDonald on symmetric functions, and so it's explained quite explicitly in there. So Jack functions, or it's also called Jack symmetric functions. J lambda B are a B deformation of Schur functions. Okay, so what does this mean? So these are some symmetric functions depending on extra variable B. But these symmetric function people like to call this a B deformation. All right, so now for B is equal to 0, so J lambda B is equal to to the classical Schur function. For B is equal to 1, you get something which are called zonal polynomials depending on lambda. And basically, these are some sort of interpolations between them. And I'm not aware of any meaning beyond those 2 values. So I don't know whether B is equal to 2 also has a meaning. I only in my life ever cared about Schur functions and zonal functions. So, but it might be. So, okay. Okay, so now let's write the corresponding tau functions. So the so-called B deformed tau function. So if tau B, and tau B we're going to define as, so this is slightly more complicated, but I promise it actually specializes to the thing that we have here in B is equal to 1. So we have some differential operator acting here and a log. And then the expression is the sum of a B deformation of this expression. So B is equal to 0 actually gives this expression of J lambda B of A times J lambda B of C, B, and I think these now should be plus 1s. J lambda B, no, sorry, the plus 1s come later. This is still B, I think. J lambda C, okay? And right, so like this is our expression. And now the question that Golden, Jackson, and so that Golden and Jackson posed is, what if I expand this in the symmetric power sums? So you can just use the classical symmetric power sums, in fact, and just take the exponent of B out. So you can move this into the world that we've already seen. And the expression that we get is the following. So this is the sum over D is equal to 1, tau to the D, and then it's a sum over the alpha, beta, gamma, again partitions of D, and now we have H alpha, beta, gamma of B times P alpha of A times P beta of B times P gamma of C. Okay, so at the moment, this is just an expression, and you can see that this actually works. So you can just expand it in this, then you get some expression, and the conjecture is the following. And this is the very famous B conjecture in symmetric function theory, which is that H alpha beta gamma is in N, so is a polynomial in B over the natural numbers. So in other words, H alpha beta gamma should count something for arbitrary B. Okay. And it's time to clean the board again. Yeah.
That's the idea that the function should take to be a polynomial with natural numbers come from the idea that it should count something, or does the conjecture of it should count something come from the conjecture that without
It's been a while since I read that paper, so I don't know whether they provide evidence for it. But of course, what you can do is you can just compute some examples, right? So for like small lambda, we have explicit expressions for the jack functions. You can just sit down and compute some examples, and then so I would expect that is so I wouldn't be surprised if this is the origin of the conjecture, and also like it. So I mean, it really counts something for the Schur functions. It's kind of a general principle that a lot of these things should sort of translate. But of course, here you're going to have something of a refined count in some sense, right? So the like count isn't going to be actual numbers. The count is going to be a polynomial in B, or you have to give some family of enumerative invariants depending on B, and then show that they are a polynomial. So in B. All right, so this is not solved yet, but in 2020, Chapuis and Dorolega made amazing progress. So by introducing something which is called B Hurwitz numbers. Okay, so what are B Hurwitz numbers? So what they did was they actually proved something more general. I'm going to restrict to the special case where the Hurwitz theory is already properly understood. So there's also some Hurwitz theory in the more general case. Well, at least I don't properly understand it yet. So maybe someone understands it, but I don't. All right. So the idea is the following. So we look at sum of the lambda. Again, we have some combinatorial factor. Now we look at j lambda b plus 1 of A times j lambda b plus 1 of B. And then here, you have another combinatorial factor depending on T. Sorry, I think, what did I call it earlier? I think I called it U earlier. So this should once again be U. And so what this is really a B deformation of the Y lambda that we had for classical Hurwitz, right? So this is like just some sort of variant. I can actually explicit, I don't want to write, I can tell you. So in the definition of Y lambda, the content formula showed up, right? Which is the column index minus the row index. So here's B times the column index minus the row index. That's it, right? So it's the very same thing. All right, and so this is the first situation, right? So okay, so we still have products of two. They did something for like a third jack function showing up, but so let's restrict to this case. And then what they showed is, I'm not going to write the entire generating series in the interest of time again, but they get something which is, like hg mu B times p mu of A times P mu of B. Okay? So, and these things right here, they turn out to be something which is called B Hurwitz. All right, so let me tell you what B Hurwitz numbers are. Okay. So here's the definition. Let F from S to P1 as for double Hurwitz numbers, right? So it's the very same holomorphic function. So with the additional constraint that there exists sigma from S to S, a fixed point free involution. So a fixed point free involution. So, and this can be orientation reversing. So a fixed point free involution such that S to S to P1 to P1. So we have sigma here, and we have F, and then down here, we just take the complex conjugation. So this is a commutative diagram. Okay, so then, right, so you look at those, and in fact you recover the classical double Hurwitz numbers as a subset. And the reason is exactly when you just take S union S to P1, right? So you just take two copies of S, and then the orientation reversing involution is just going to like collapse both of them. That is basically what's going to happen. Okay. Right, so like what you just do is you map S to P1, and then you take a second copy, and then you sort of map it with respect to the other orientation to P1, and then the quotient S mod sigma is just going to be, well, S union S mod sigma is just going to be S. So you do actually recover double Hurwitz numbers. Okay, so this is what is called a generalized Hurwitz cover. Okay, so then Chapuis and Dolega, they proved so they did the following. So they introduced. Oh, did I ever write their names? No. Okay, so I should write their names once. Chapuis and Dolega. Right, and this is like some sort of this like Polish letter with a, I don't know how to write it. It's an L with a line. So they found a way of measuring how non-orientable F from S mod sigma to P1 mod the equivalence relation Z corresponds to its complex conjugate is. Right? And this is called nu of F. Right? So this is the so-called measure of non-orientability. And the way this is done is you take a graph on P1, you pull it back, and then you just like track how many times edges change orientation when moving from one vertex to the other. So this construction is quite involved, but the important message is they found a way of measuring like how non-orientable these things are. And the theorem they proved, and this is, I think, really quite amazing, is that these Hg mu nu B, they are the sum over F, a generalized Hurwitz cover. And then, so instead of weighting them by 1, so just counting them, they weight them by B to the measure of non-orientability of F. So meaning the higher the exponent of B in the polynomial, the more non-orientable it is, or the less orientable it is. Okay. So how much time do I have left? 8 minutes. Okay, I can do this. All right. So okay. So like this is their theorem, and this plus what they did extra is the most progress that has ever been made towards the Golden-Jackson B conjecture. So this is really the current state of the art. Yeah. Yeah, so this is a little complicated. So what you do is you draw a graph on P1 on the equator. So you fix all the branch points because, right, so like sigma is fixed point 3. So all the branch points downstairs will have to live on the equator. You just draw the graph on the equator, which connects all of the vertices. You pull back that graph to S mod sigma. So you actually don't pull it back to S, you pull it back to S mod sigma. And then what can happen, right? So let's say you have like 2 faces in that graph, and then these faces are connected by an edge, right? So what can happen is, and so like typically, okay, let me draw it like this. So typically this is drawn like this because you can have this picture, right? So left and right, locally at this vertex, so it tracks along this edge. Or what can happen is that you have 2 faces, you draw these things, and then the orientation of left and right at the vertices is sort of reversed. So this gives a multiplicity of 1, and this gives a multiplicity of b. Right? So just measure like how often, basically, it's a little more involved than that, but the basic idea is you just measure how often edges flip orientation in the graph. Right? Sorry? Basically, yeah. So, and this is really quite a genius idea, I must say. Like when I read this first, I was very confused, but then when I understood it, it's like really, really quite clever. And so what's cool is you can actually define all sorts of measures of non-orientability. So there's a bunch of them, but they all give you the same Hurwitz numbers. So this is really some sort of magic that's going on. What? Because it's the B conjecture. What? Because Jack functions are traditionally called B deformations. I don't know. So they're also called alpha deformations, but B is equal to alpha minus 1. I'm sorry, this is really not helpful. I understand. But I don't know whether there are A deformations. I actually don't know where this comes from. So no, like this is a like natural number. That's a natural number. So including 0. So, and this is 0 if and only if the map is actually orientable. Right? And therefore for B is equal to 0, right? So like B to the 0 becomes 1. So for B is equal to 0, all the higher degree terms vanish. So you actually will recover classical Hurwitz numbers. And then, yeah, so in the interest of time, I'm going to skip some stuff. So we come to section 4. So what about tropical? Okay. So, and now this is where Hannah and I sort of started. So we fixed it. So we fixed B is equal to 1. So, and there's a bunch of reasons for this. So first of all, B is equal to 1 just actually counts all of these Hurwitz couples, these generalized Hurwitz couples, right? So like everything is counted with, right? So it's just like 1 to the something. So this is just going to be 1, right? So you simply count these Hurwitz covers, and so you kind of integrate this like real world in this real in the sense of real numbers and real algebraic curves into this tropical picture. All right, so here's what we proved. Okay, so I should mention, so there's work by Berman and Fessler. So Fessler being the one that is now part of this, well, so we're like joined towards a like joint program. So they found a symmetric group interpretation. Okay, and sorry, and so for B is equal to 1. And this is actually quite hard. So what happened was that they actually solved the problem in surgery theory. So you had a bunch of spheres, you glue them together, and then you count how many ways this is possible. And then they derived the differential equation that the generating series of like their numbers satisfy. And then they like submitted the paper, and the referee told them that it's the same generating series as you get here for B is equal to 1. So, and then you can show that the initial condition is the same up to a factor of 2 to the something. And so therefore their interpretation in surgery theory corresponds to the interpretation for B is equal to 1. We currently do not know, so we're trying, but we currently do not know how to transfer the measure of non-orientability to the symmetric group, because this is really quite a complicated problem. Even getting a direct correspondence for B is equal to 1 is like a 30-page paper, and it takes a lot of work. Okay, so what we proved is the following. And then we sort of generalized stuff earlier this year to elliptic targets. So Hg1 of mu nu is the sum of in the interest of time, I'm just going to write what it is, and then I'm just going to draw a picture. So weighted sum of tropical covers with an involution. All right, and basically I want to draw you a picture. So what this picture looks like is this. Right, and again you have the balancing condition. So this is still satisfied, but so a bunch of differences. So I of course drew this in a suggestive way. This is the involution, right? So you just flip things. So you can have 4 valent vertices, right? So this is a vertex, and 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 this. So this is just my lack of capability of drawing. So maybe more like this, right? So, all right. Yeah. So you have four valent vertices, and so the edge weights. So the weight is still a product of edge weights, but you also get vertex contributions here. So now here's something that's interesting, right? So classically, so if you look at this, and I just take the quotient map, right? So let me trace this as a remark. Let's say F bar, which is S mod sigma to P1 mod the complex conjugation. So this actually completely recovers P. Completely recovers F by taking the orientation double cover. All right. So this is not true tropically. And I stress this because we thought for a long time that this is true. But what we can do is, right, so you can just take the quotient, and you would maybe expect you can just reconstruct this tropical structure, but it's not true. And so if you do F trop bar from gamma bar to the projective line, so what you get is, so this I always have to, so this has 2 to the G prime of gamma bar. So this is just a genus of gamma bar, and then 2 to the number of 4 valent vertices times the automorphisms of the tropical map downstairs, right? So of this quotient map, many lifts. All right, and I'm already over time. Let me say one more sentence. So there was a polynomiality result proved in Chapuis and Dolega. And at least for B is equal to 1, these tropical methods actually improve that polynomiality result. So there was a sort of like artificial factor appearing that we know from classical Hurwitz theory shouldn't be there. At least for B is equal to 1, tropical geometry resolves that factor. So you can actually just get rid of it. All right, and that's my talk. Thank you very much.